Good morning, everyone. Thank you for coming. My name is Bob Steagall, and I'm here today to talk about a little bit of code I wrote, an experiment I performed for doing multi-threaded transaction-based locking on vectors. And I've developed an algorithm. I'm not sure that it's new, but I think it's new. And this talk is about that algorithm. So we've got a lot to go through. I'll jump right into it. So sometimes when we're doing work, we have a multi-threaded application and we need to share a container amongst multiple threads. So I'll talk about the motivation. I'll talk about some solutions. I will then describe my solution, which is based on a concept called strict timestamp ordering. I'll talk a little bit about the testing and show some test results and summarize. So sometimes we have a multi-threaded application and we absolutely need to share it amongst threads. And if we need to write to that container, we want to avoid race conditions. We don't want to have corrupt data. So for the algorithm I'm about to describe, I'm going to assume that elements themselves, elements in the vector, are themselves unsynchronized. They are susceptible to races if two threads try to write to one element simultaneously. I'm going to assume that we want to update an element, only one thread can update an element at any given time. And that no other thread can read an element while the writing thread is updating it. However, more than one thread can read an element when that element is not being written to. In modern C++, we have a lot of concurrency tools that are now available to us. And I think that writing multi-threaded applications is easier than ever. Maybe easier. So if we have this situation where we have multiple threads trying to manipulate a container, if all of the threads are readers, then we don't need any locking on the container. And if we have a situation where we're writing to the container and the number of threads that need to read the container is much larger than the number of threads that need to write to the container, then we might be able to use a reader's writer lock like stood shared mutex. However, the situation sometimes arises where most of the operations that you want to perform on the container are write operations. Now, in this case, when you start thinking about the design that you want to implement, you might think that a per element mutex strategy might work. And it might work if a given write operation requires locking exactly one element. But what about the case when all the operations are writes? Sometimes you have a situation, and I was working in a situation a year or so ago, where all of the operations that were performed upon this set of containers were writes. So what if they're all writes, and each element that you want to update is also related to some other set of elements that are members of the same container? So let's call this set the related group of E. In other words, you have an element E and there's a group of related elements. And let's define the update group of E as being the union of E's related group and E itself. So in graphical form, suppose that we have a set of elements. Here I've just listed 16. And I want to update E, and this is transaction N. Well, E8, which is the index of the element, is related to element 2 and element 11. And element 2 is related to element 1 and element 5. So by transitivity, the related group for E8 consists of E1, E2, E5, and E11. In other words, if I need to update E8, these are all the other elements I may need to touch that I may need to update in order to successfully update E8. So the update group for E8 is going to be that set of related elements plus E8 itself. So going back to our conditions, now that we know what an update group is, suppose also that one of the elements in E's related group also has to be updated at the same time, consistently with E, not only read, but updated. And the number of elements in the related group varies from transaction to transaction, and the membership of the related group can possibly vary from transaction to transaction. In other words, in transaction N, I have a related and update group for E that looks like this. But if I go to transaction N+1, perhaps even the next transaction, and I need to update E8 again, perhaps the membership of the related group has changed because of the update that I did in transaction N. So why did I try to solve this problem, and why is it interesting? Well, suppose that I have a thing that I choose to label a reactive message processor. It's a box, it's a program that receives a continuous stream of input messages, perhaps from Kafka or something like that. And it listens to these messages and it generates output. Perhaps it sends that output to another Kafka instance somewhere when something interesting happens in the stream of input messages. So how does it know if something interesting has happened? Well, when messages come in, the stream processor, the message processor, has to keep a history that has pertinent information about the messages. And each message comes in, the message processor takes the incoming message, compares it against the relative aspects of the history, and decides whether or not something interesting has happened so I can send a message out. In this particular case, I don't actually need to read the state of the history. Every message that comes into the message processor requires a write operation into the history. And the history, as I mentioned, in the work I was doing before, can be one or more containers. In the code that I'll show you today, I'm just using a single vector to demonstrate the algorithm. So here's a diagram of our reactive message processor. We have our input source, we have messages that come in, we process the messages, we look into the history, we pull some data back out, we decide whether or not we need to evaluate, and in the process of evaluation, whether or not we've created an interesting message, if an interesting change has happened, and if it has, we send it out to the sink. This is pretty easy to do in the single-threaded case. However, in the work that I was doing previously, we needed this to scale to multiple threads, and not just a couple of threads on the order of a few tens. So it really sort of looked like this. Here we had our source feeding messages into a number of threads, and each thread running its own message processor, and each message processor was putting changes into the history and seeing if anything interesting happened and sending it out to the sink. Now, the interesting thing here is that there are multiple instances of the message processor, each running in its own thread, but there's only one instance of the history, which was in the same process. And of course, all threads in a process share the same address space. But the history was in effect a singleton, and all of the threads were reading to and from it. So what do we want our solution to be able to do? What are the properties we look for? Well, first we want updates to be atomic. And when an update group is modified, we want the modification of that group to be treated atomically as a transaction. And as a transaction, it either succeeds completely or it fails completely. The state of the history, the state of the container, has to be consistent from transaction to transaction, meaning that when a transaction occurs, it can only take the update group from one valid state to another. And of course, if the transaction is rolled back because the update can't be performed, then I'm going from the previous valid state back to that state. And we also want transactions updates to be isolated. In other words, every time a transaction occurs, that transaction has to occur and leave the container in such a state that might have been obtained as if all the transactions were executed in some unknown but valid sequential order. So multi-threading and concurrency must not affect the atomic nature or the consistent nature of the state of the container at the end of each transaction. So what are some ways that we can solve this problem? Well, the first thing that might come to mind is a per container mutex. We create a container, we create a mutex for the container, and we perform updates in a single critical section that's guarded by the mutex. The upside to this is that it works. It's easy to understand and it's easy to reason about. The downside, however, is this does not scale. Another solution that people look to in situations like this is called sharding. And sharding is where you divide the set of elements in the container into individual, in a sense, self-contained groups called shards. And each shard has the members of every related group of every element that is in the shard. So if there's some element E of n that's in the shard, all of its related group is part of the shard, and that relationship holds for every element that's in the shard. So in this case, you can have a situation where updating the shard is performed by a single thread that's dedicated to servicing that shard. And in effect, there is no locking because there's no need to lock, because we know by design that only one thread is going to be writing to or updating that particular shard. The upside to this is you can get good performance. However, the downside is that it increases the complexity of your solution. You have to manage your containers and manage your data appropriately. And also, it works if and only if the data itself is amenable to sharding. Another idea that you might have is having a per element mutex. In other words, every single element has its own mutex. And in order to perform an update on an update group, you acquire all the mutexes for all the elements in that update group. You do the updates, and then you release them all at once. The upside to this is it seems like it ought to work. And at least it seems like it should work for the case where the update group has exactly one element, which is E, the element you're trying to update. It's a little more difficult to understand and think about. The downside, however, is some mutex implementations are not small. POSIX pthread mutexes are pretty big. But the tricky situation is what happens if you have an element E0 that you want to update, and its related group contains element E1. And concurrently, another thread is trying to update element E1, and E1's related group contains E0. Well, now you're going to have an order of operations where you end up with a deadlock. Obviously, we don't want this to occur. So the per element mutex is kind of like a mirage in the desert. You think it might work, you think it's there, but it really isn't. So as I was trying to solve this problem, I came across, and having done a tiny amount of work with some databases in the past, I remembered this thing called timestamps. So I looked and found an algorithms based on the concept of something called strict timestamp ordering. Now, strict timestamp ordering, or STO, is one of a large variety of database concurrency control algorithms. There's a whole wealth of them out there, and STO is one of the first ones they teach you when you learn about transaction processing in databases. So it's a transactional algorithm, and as the name suggests, it is timestamp based. So what's a timestamp? Well, a timestamp is a monotonically increasing value, usually an integer value, that indicates the age of a transaction. So if you have a timestamp value that's lower, that means it's an older transaction. If you have a transaction value, a timestamp value that's greater, that means it's a newer transaction. In essence, the timestamp value is very much like the birthday of the transaction. So the idea behind STO is that it uses timestamps as the basis of serializing concurrent transactions so that we avoid race conditions and that we fulfill the conditions of atomicity, consistency, and isolation. So in general, when a transaction begins, it's assigned a unique timestamp. And for this to work correctly, the timestamp has to come from an authoritative universal timestamp source. Every entity that's using a timestamp has to agree on where they're getting timestamps from. Now, if two transactions are trying to update or write to the same update group at the same time, the principle is the transaction with the lower timestamp, the the older transaction goes first. Younger transactions always wait for their elders, and older transactions never wait for younger transactions. Instead, they roll back, they give up, and they try again. So very smart people have proven that STO operation schedules, in other words, the order of operations in which updates are done in STO-based systems, are serializable and deadlock-free, which are, great properties to have for our problem. However, as probably apparent from the previous bullet, the price that you pay for this power and this freedom is that it's possible that a thread who's trying to do an update could starve and have to restart the transaction. And you might be able to get into a situation where a thread trying to do an update keeps trying to update. By the time its turn, realizes that a younger transaction has actually already updated and has to go back. So there could be some starvation in this case. So talking about the algorithm in the general case in just a little more detail, let's suppose that we have some element E, and associated with E, we have a read timestamp and a write timestamp value. And TSV is the nomenclature I use here to indicate timestamp value. So if you have a transaction, let's call it TX1, and it has a timestamp TSV, let's assume that it has functions begin, commit, and rollback. And there's a facility for transactions to acquire elements. Acquire might be a function or it might not, but there has to be a way for a transaction to say, this element is mine right now. Let's assume that as part of our business logic, we have a function to update E, and we have a function that reading from E. So let's look at the read case. Transaction wants to read the element. If the transaction T1 finds that its timestamp is less than the last write timestamp in the element, that means a younger transaction is already written to E. So the transaction T1 rolls back. If transaction finds that its timestamp is older than the last write, that could possibly mean that an older transaction is in progress. So transaction TX1 will wait until all the older transactions, in our example here, TX0, are done. Then TX1 will acquire the element, it will assign its timestamp value to the read timestamp, and it will read E's contents. It then releases E and goes on its way. Writing is a little more difficult. As with reading, if I'm trying to write and a younger transaction is already written, has already read from E, that means I have to roll back. I can't write to a transaction, I can't write to an element if a younger transaction has already read from it. If my timestamp value is less than E's write timestamp, that means a younger transaction has already written to E. So again, if a younger transaction is already written, I have to roll back and start again. And as before, if my transaction value, timestamp value is greater than the write timestamp for E, that means an older transaction might be in progress. I wait until all the older transactions are done, and then I acquire E, I update E's write timestamp with my timestamp, and I update the contents, I release E, and I go. In our case, we only have to worry about writes because that's part of the problem here. All of the changes to the container are update operations. So we only need one timestamp per element. So in this case, every operation that we want to perform is an update. So when our transaction calls update, if a younger transaction is already written, to the element, we roll back. And as before, if an older transaction has written to it, it might be in progress. We wait for the older transaction to complete. We acquire E, we assign to it, we assign our timestamp to E's timestamp, and we update E and go on. So in order to do this, we need some basic synchronization components, which modern C++ provides. We need a mutex, we need a condition variables, we need atomic pointers, and we need the ability to do atomic compare and exchange on pointers. We need a class that represents a lockable item. i.e. the element that I've mentioned. And we need a class that manages transactions on behalf of each thread. And in this design, transactions are not actually objects. Transactions are ephemeral things. They don't live very long. And it just turned out, I found, to be easier to have a manager class that is long-lived, that has the life of the thread, and that is responsible for managing transactions. Transactions themselves are represented by a timestamp value. So when a transaction is in progress that has that timestamp value, in a sense, that transaction is alive. When the transaction manager's timestamp value changes to the next timestamp that it acquires, the previous transaction is done and the new transaction begins. So threads share a container or containers that hold the lockable items. Each thread initiates its own transactions, and each thread owns the transactions that it initiates. Each transaction's key operations, beginning the transaction, acquiring the transaction, committing and rolling back the transaction, can only be performed by the thread that owns the transaction. In other words, the transaction manager. The transaction manager acquires the lockable items, it locks them on behalf of the owning thread, and then other logic, the business logic that actually does the process of determining the update group, updating the update group, is part of code that lies outside the transaction manager. In any transaction, we have to acquire, because we may need to write to every element of the update group, we have to acquire all of the members of the update group before you can do any write operation to any member of the group. So here's some pseudocode that I'd like to walk through very quickly that describes the algorithm at a high level before we jump into real code. So let's assume that we're starting a thread function, and one of the arguments to that thread function is a reference to our shared collection. The very first thing we do in the thread function is we create the transaction manager. Once the transaction manager starts, we begin looking for work to do. So let's assume that there's work that needs to be done. All right, there's work left to be done. We're going to begin a new transaction. All right. So as part of that transaction, we've determined that there's some target element in the shared collection that we're interested in. So the first thing we'll do is we will try to determine the membership of the update group to the greatest extent possible. Then we will, in a sense, recursively or iteratively look through the update group. So while update group members remain unacquired, there could be more update groups in a transitive relationship, and all of the acquisitions that we performed have succeeded so far, we will start to acquire the next unacquired member of the group. We revise the membership of the group, and we go back up again. And so what this loop is indicating is that you start with E and you keep iterating until you find all the members, you compute the set closure of all of the elements that are part of the update group of E. Once that's done, if we are able to acquire all the members of the update group, then we apply our write operations to that group. We commit the transaction, and we go do new work. Otherwise, if we were not able to acquire all the elements of the update group, we roll back the transaction, we loop back to the top, and we try again. So let's look at some prerequisites for the code. So here's a little bit of the header. And as we go through the code, you'll see that there's some areas that I've highlighted in yellow. And those are the things I'd like you to pay attention to. So of particular importance here in our forward declarations header are the timestamp value type, which is an unsigned 64 int, a forward declaration of the transaction manager, and a forward declaration of lockable item. So let's look at the lockable item class. So here's the class declaration. It's intended to be used in these demo programs as a base class. So it can return its ID, which is not relevant to our discussion. It can return the last timestamp value. But of particular interest is the fact that its friend class is a transaction manager, and it's interested in an atomic pointer of type transaction manager star. It maintains an atomic pointer to a transaction manager, and it also maintains the timestamp value of its last owner. And this is important. This is how we know, this is how we determine who is the last updater of this element. And this is how an element knows, the atomic pointer tells the element who owns me right now at this moment, or who has locked me at this moment. And here's some of the code for that very simple class. I only bring it up because here's the interesting stuff. We start with a timestamp value of 0. So every timestamp, no timestamp can be 0. 0 is the null timestamp. The first valid timestamp is 1. And we initialize the atomic pointer to the transaction manager with a null pointer. And we're using the convention here that a null pointer means I am currently unlocked. No one currently owns me at the moment. So now let's dig into the transaction manager class a little bit. This is a little bit longer, and it contains member functions that you might expect it to have. It has a begin, a commit, a rollback, and it has acquire an element. And here we're passing a reference to a lockable item. As I mentioned, lockable item is intended to be used as a base class. So we acquire it with a reference to the base class because the base class has everything in it that we need in order to do the locking. These member functions, which are part of the transaction manager, are part of its public interface. And they are intended to be used by the business logic in the rest of the thread that's attempting to do the updates, to acquire the update group, to update them appropriately, and then commit or roll back as the case may be. So let's look at dig in a little bit to the implementation. Here I've highlighted in yellow just some simple type defs that I've created to make the code a little easier for me to read. And here are the relevant data members relevant to this discussion. We have a timestamp value. This indicates the timestamp that is current. This indicates the transaction that is currently in progress. I have a list of pointers to items. So here is my vector of pointers to lockable items. And so this vector of pointers to lockable items to elements, this indicates the members of the update group. I have a mutex, which I mentioned before, I will use for locking, and a condition variable that I'll use for waking threads that are waiting for a transaction to complete. And finally, I have here I've defined an atomic TSV. It's an atomic unsigned 64-bit integer. And here I've defined a static member, which is the generator. This is, in effect, the authoritative universal source of new transaction timestamp values. So the picture I'd like you to keep in your mind is this. Here I have two different threads in my very simple diagram. Each thread has its own transaction manager, and each transaction manager has the list of lockable items which are currently members of the update group. The list of lockable items has pointers which point to the relevant elements that are members of the update group, and each lockable item points back to the transaction manager so that the element that's being locked knows which transaction has locked it. And here I've just drawn it in a simple way such that the threads or the ownership directions don't overlap with each other. But you can imagine this played out over a larger number of threads, and with these ownership relationships from the lockable items to the actual elements being spread over a large array of items. So here's our implementation of the static variable. That's our timestamp value generator. Here's our constructor. And so what I'm doing here, this is the important and interesting initialization. I'm setting the timestamp value. I'm initializing that atomic integer to be 0. I am going to initialize my array of pointers to items. And in the body of the constructor, I'm going to reserve 100 because it just seems like a reasonable number. In the work that I was doing before, the levels of transitivity in those particular relationships were never really more than 3 or 4. And the total number of members in an update group was really never more than 20 in practical circumstances. Here's my mutex that I'm going to use to guard shared state. And here's the condition variable I'm going to use for broadcasting the completion of a transaction. So returning the ID and timestamp value, those are not very interesting. So here's my begin. And this is important. When I begin the transaction, I'm going to acquire the lock in my own mutex. And the reason for this will become obvious later in the code. I'm going to acquire the lock of the mutex that I own. Then I'm going to atomically update the timestamp value. I want this to be atomic because if some other transaction is doing it at the same time, I want the 2 transactions to receive 2 different distinct values. Once I've updated my timestamp value, I'm going to unlock the mutex that I own, that's a member in my data. Here's the logic for commit. It's a little more complicated, but it's analogous. Before I can commit a transaction, I have to lock the mutex that's part of my member data. And then while I still have elements that are members of my, while I still have items that I own that are members of the update group, I'm going to set the owning pointer in each of those elements. I'm going to atomically set it back to null, meaning this element is no longer owned. And then I'm going to pop it off the back of the array. So at the bottom of this array, for all of the elements that were part of the update group, I have set their transaction manager pointer back to the null pointer atomically, indicating that no one, these elements are no longer locked. And finally, at the bottom, I will broadcast on my condition variable. I will notify them all, in effect, releasing them. If anyone is waiting for this transaction to be done, this notifies them that the transaction is done, and they can go back and try to acquire 1 or more members of that update group. And of course, as I drop out the bottom here, the lock, the lock, guarded lock, unique lock destroys, and the mutex is released. So acquire is the function that was most difficult and trickiest to implement. And so what I'm going to do in the next few sections is I'm going to show you pseudocode for the algorithm, and I'm going to interleave it with the real code, and hopefully it will make sense as I do so. So I've initiated a transaction, I've begun a transaction, I have my first element, I know what my first element is, and now I need to acquire it, right? And I need to subsequently acquire elements in the update group. So I will loop. If I can acquire an item, meaning no one else has locked it, I'm going to add that item to the list of items that I own, the list of lockable items. If my timestamp, having acquired this, if my timestamp is newer, meaning it's higher than the lockable item's last timestamp, I'm sorry, if my timestamp is newer, that means that an older transaction is written in. So if my timestamp is newer, the older transactions are done. I set item's timestamp to my timestamp. I mark this as a success, and I keep going. Otherwise, if my timestamp is older than the item's timestamp, that means a younger transaction has updated it, and I roll back and go back to the top. Now, if I don't acquire the item, if I'm not able to acquire the item, it could be that I already own the item. If I'm computing the set closure, it could be that for some traversal over elements, I will encounter the same element twice. So if I already own the element, well then that's success and I go back. Otherwise, if I'm not able to acquire it and I don't already own it, I wait for the current owner to release the element, and then I go back and try again. So what does this look like in real life? All right, well, here's some real C++ code, and this is in the demo code. This code that I'm going to show you corresponds to this part. If I acquire an item, I add it to the list of items that I own. So I've got a pointer to a transaction manager. This is I will use this pointer to represent the current transaction manager that owns the item. In other words, when I acquire an item, if I'm looking at the item, someone else might own the item. So I'll do an atomic compare and exchange with the null pointer and with a pointer to myself, because I'm a transaction manager. So for those of you unfamiliar with it, atomic compare and exchange is a special atomic operation. And here we're very fortunate that it's implemented for pointers, and we're taking advantage of that. So paraphrasing CppReference.com, atomic compare and exchange compares the representation that's stored in the atomic pointer with the representation that's in expected, the first argument. And if those are bitwise equal, it will replace the representation that's part of the atomic pointer itself with the value of, replaces the representation of this, the representation that's in the atomic pointer, it replaces it with desired. Otherwise, it loads the actual value that's stored in the atomic pointer into expected, and it returns false. So if we go back and look at this, what this really means is I'm going to call compare exchange strong. What I'm hoping for, what I expect is going to be the value in that pointer is the null pointer. I expect that that element is going to be unowned. And if this returns true, that means that my expectation was met. The current value, or the value that was in that element, was the null pointer. And so compare exchange strong will now swap that value. It will swap the value of a pointer to me into that. And it does that compare and exchange in one atomic operation. So if this succeeds, then the pointer to the transaction manager that's stored in the lockable item points to me. I own this item now. Now that I'm sure that I own the item, I'm going to push that pointer back onto the back of my list. I then go to this part. I'm going to check the value. I'm going to look at the value and make sure it's a good value. So if my timestamp value is greater than the timestamp value in that element, I'm going to set the timestamp value to be me. If not, I'm going to return false. If I return true, that means I acquired the item. If I return false, that means I did not. Okay? Well, suppose that I did not acquire the item. Suppose that the null pointer was not the expected value, right? The pointer that was stored in the lockable item was pointing to something else. I don't know what that something else is, so I need to determine whether I own it already or somebody else owns it. So I drop down here. If that pointer, if I already own the object, that's great. I return true because I've acquired it already. Otherwise, this is where things get subtle. So what I'm going to do, I know at this point that the pointer in the lockable item is actually pointing to a transaction manager, but it's not pointing to me. It's not pointing to the transaction manager of my thread. So I'm going to try and lock the internal state of that other transaction manager. I'm going to try to acquire his mutex. When I do acquire his mutex, I'm going to look and see. I'm going to look and see in the item if it's still owned by that transaction. So I know what the item is. It was an argument to the function. I'm going to lock that other transaction manager. I'm going to see if that transaction manager still owns that item. It could be between the time I did this comparison and the time I got here that the other transaction released that lockable item. So I'm going to check to make sure that he still owns it. If he does still own it, I'm going to look at the timestamp value. And if he was a younger transaction than me, then I'm going to return false because a younger transaction is updated and I have to try again. But if it is not a younger transaction, then I'm going to wait for him to complete. I'm going to wait for him to complete the transaction. And I'm going to wait on the condition variable that I know he has because I have one too. So there, I check the ownership. I look to see if the timestamp value is valid for my purposes. If not, I return. Otherwise, I wait. Now remember, this is what commit looks like. And let's pretend that this commit is being called by a transaction manager in a different thread than me. Well, he is busy committing. And when he commits, he's going to release all of those guys, all of those items by setting their ownership pointers to null. And then he's going to broadcast on that condition variable. And when he broadcasts on that condition variable, I'm waiting on him. I will go back up to the top. Now, while I'm in this section, while I'm in this loop, I'm still in the critical section from this mutex. So there's no possibility of a race condition looking at his internal state. So I run this, and if I don't succeed, then I go back up to the top. Or succeed. I go back up to the top and retry. That's the point I was trying to make. So let's look at how we test this. And I'm going to show you some test code. I know nobody likes to look at this, and some performance graphs. The interesting part of the test code I'm going to show you shows some business logic that I had to write to support the idea of figuring out the update group, updating the update group, and then committing the transaction. So let's outline our test strategy. So we need to create some functions that are going to update a collection of shared items, right? We want to make sure that, having done this, that we write our data in such a way that race conditions are possible if our algorithm is invalid. So we want to make it easy to detect race conditions. When we're doing measurements, we want to measure single-threaded updates. In other words, if only a single thread is going out and doing the same business logic, how fast does that run? And then we want to measure the multi-threaded updates in a situation where we're doing the same logic as the single-threaded updates, but we're doing it in multiple threads. We're not guarding access to the elements, and we're trying to cause data races. And I've designed the test element in such a way that causing a data race won't cause a crash. And for comparison purposes, we also want to measure multi-threaded updates that are guarded by a single critical section. And in this case, because we're not distinguishing between readers and writers, we don't really need a shared mutex. We can just use a regular mutex because every operation is a write operation. And then finally, we want to test the algorithm's performance by measuring transactional updates in a multi-threaded environment. So the system that I ran this on was an 8-core Intel CPU, so 8 cores, hyperthreading enabled, 16 hypercores, running Ubuntu 18.04, and I used GCC 10.2, the most recent release, to build the demo program and run some test driver scripts that collected the results that led to the graphs you'll see in a few minutes. All right, so I'll walk through some of this code quickly. Here are the prerequisites, and of importance here, I'm going to create a list of items, and I'm going to use random number generation. I'm going to use random number generation to generate data, and I'm going to use hashing to verify the validity of the data that I've created so that I can detect a race condition when it occurs. So let's look at our test item. As I mentioned before, lockable item was intended to be used as a base class, and so that's what I'm doing here. I'm going to use a buffer size of 32, and in my item, I'm going to contain a buffer of 32 characters. This is the thing that's going to get updated. I'm going to have 2 member functions, single-threaded update and transactional update. So single-threaded update is a little bit simpler. Let's look at it first. When I do a single-threaded update, I'm going to create a local buffer of characters. And then for ease of use, and because I was playing around with string view, I'm going to create a string view that refers to my local buffer of characters, and I'm going to create a string view that refers to the character of buffers that are member data of this item. So I have member data, which is possibly shared amongst threads, and I have local data, which is only visible in this thread. And so what I'm going to do is I'm going to update the local data and the data that's member data at the same time in this simple loop. Now, in the single-threaded case, this will work correctly. And when I hash the data in the shared view and I hash the data in the local view, I will get the same answer. But when I don't get the same answer, I found a race. And the reason I found the race is while I was doing this, and before or even while I'm computing the hash value of the shared view has changed and its hash value will be different. So this is how I detect race conditions, by creating a local copy, hashing it, and looking at the hash value for the shared copy. TX update, which is used in the transactional case, is very similar. It's almost identical, except it is passing in a value a reference to the transaction manager. Sorry, that's a typo. It's passing in a reference to the transaction manager, and it's passed that in so that when it does logging, it can report the ID of the transaction manager where the race was found. And because that ID is a const member function of the transaction manager, which is only created when the transaction manager is instantiated, there's no possibility of a race condition by reporting the transaction manager's ID. So once again, local copy of data, string view that points to that, a string view that points to the shared member data. Update both at the same time, compute the hashes of each, and if the hashes are the same, there's no problem. If the hashes differ, there's a race. Okay, so let's look at the actual test that's being performed here. This test function, TX access test, this is a thread function. This is the function that's running in a thread that I mentioned before previously in the algorithm. So here I'm setting up some data that I'm going to use to implement my business logic, including some random number generation here. I'm going to have a stopwatch to do timing. I'm going to keep some data which represents my update group. Importantly, this index list, this is a list of this is how I will form my update group. And here I'm creating a transaction manager. So here I'm giving him, I'm forgotten what the one refers to. That might, yeah, I've forgotten what that means. Anyways, I'm creating the transaction manager and I'm keeping a Boolean value that will effectively keep the summation of, oh, I'm sorry, the one is the log level, the logging level. So I'm keeping a Boolean value to keep track of the totality of whether or not I've acquired all the elements in the update group. So, well, let me go back, and I forgot to highlight this. I'm going to start the transaction. So I move past this, I start the transaction, okay. I'm going to clear out the data that I used to compute the update group. And then I'm going to compute the membership of the elements that comprise the update group. And I do this by generating random numbers that correspond to elements that are in the array of data. So the update group is basically always the same size in this test, but the membership of that update group varies from transaction to transaction. So begin the transaction, I acquire the data, or I set my acquired flag as being true. And then what I do is I start trying to acquire the data that's in my list of elements that are in the update group. So I form the list of elements that comprise the update group. Now I'm going to iterate over that list and I'm going to try and acquire each one. If I successfully acquire it, I will loop through and I'll keep going until either I failed to acquire or I've acquired every member, whatever the number of references, the number of members that I've decided I want to acquire. I step out of the loop. So if I've acquired it, then for each item that's part of the update group, I'm going to call TX update, the transactional update function that I just showed you above. That's going to write data into the local buffer and the shared buffer and compare the hashes and look for a race. I'm going to do that until I'm done. Then I will commit the transaction. If I can't do that, if I am unable to acquire all the elements in the update group, I will roll back. And at the end of this, at the end of the lifetime of this function, I'll then print out the statistics of how much time I spent running in the function. So let's look at some test results. So here's a test that I ran where the number of elements in the lockable items collection was 10 million. So there were 10 million items that were part of the shared collection. I ran 100,000 transactions. Each transaction had an update group that had 20 members in it, and I ran it from 1 to 16 threads. Now, you may look at this graph and you may say, well, what does this 0 mean? So the 0 is the special case. 0 is the baseline case in all of these graphs. 0 represents the case where I was only doing a single threaded test in a single thread. There was no multi-threading, no transaction involved. It should be the fastest possible result. And basically it is across all of these. Then I ran the test for 1 through 16 threads using the transactional algorithm. So you can see that there is a little bit of overhead here doing the transactional algorithm in one thread versus doing the same operations in a thread that has no transactions. So I did it for 1 to 16 threads, and here are the number of, this is the test that I ran where I was deliberately trying to find race conditions. So it's labeled races. So I misspoke. This particular graph shows the case of attempting to find race conditions. So in this case with 10 million elements, for each number of threads, the number of races that I would find where a transaction, 2 transactions were trying to update the same element at the same time was very small. The next case was running for a single mutex. In other words, if I was only using a single mutex to guard all accesses from 1 to 16 threads, what does the performance look like? How long does it take? So you can see again from the single threaded case to the multi-threaded case where everything is locked with only one thread, there's a little bit of overhead difference here. And then you get a nice linear progression here because every thread is doing 100,000 transactions. Because there's sequential access to the collection, you would expect this to be linear or close to it. When we get up around 13 threads, on this particular computer, I saw this very strange behavior where 14, 15, and 16 threads would actually update more quickly when there was a single mutex. And this behavior was somewhat consistent across all of the runs on this particular computer. I can't explain it. I don't know what's causing it, but it might, perhaps my theory is it has something to do with hyperthreading, because this machine had 8 physical cores, but 16 hypercores. So perhaps hypercores had something to do with this phenomenon. So finally, for this case of 10 million items and 100,000 transactions and 16 threads, here is the timing. So you can see there's a little more overhead for a transactional case with 1 thread versus no transactional processing. But the amount of time that was taken to do 100,000 transactions in each thread has only multiplied by a factor of about 2. So I've increased the amount of work that needs to be done by 16 times when I go from 1 to 16 threads, but the amount of time, the amount of wall clock time taken to do that work has only increased by a factor of about 2. Now, the subsequent graphs I'll show you, I'm decreasing the size of the collection in order to try and force more collisions in the data. So here again, I'm looking for more races, except I've got a smaller collection of items, 1 million items. And here you can see with fewer items, the probability of causing a race has increased. And so you see more races for each number of threads, and you kind of expect this behavior. As there's less data in the collection, the probability of a race condition occurring improves or increases. And so that's what this graph shows us. Again, in the case of locking the data with a single thread, the performance curve is very similar, or locking the data with a single mutex. The performance curve is very similar. When we get out around 13 threads, the behavior is strange. And the transactional case. So again, in the transactional case, I would expect that the number of rollbacks would also increase as the number of collisions, or as the number of elements in the collection decrease, because the probability of two transactions having a given element be the member of update group for two different transactions increases. So we see the number of rollbacks in absolute terms is a little bit higher. But the performance delta is still, I'm doing 16 times as much work in 16 threads, but my wall clock time is only doubled. And similarly, for 100,000 items doing races, for 100,000 items and 100,000 transactions, the number of races goes up and the curve starts to get a little smoother. For the case of guarding with a single mutex for 100,000 items, again, the same strange behavior out around 13, 14, 15, 16 threads. And for the transactional behavior with smaller number of items, you can see that the curve for the number of rollbacks is now starting to climb. And that means that there are more collisions. More collisions means more rollbacks, which means more work for the transactional algorithm to do. So you can see that there's an inflection point here, and the time that takes for the transaction actually starts to climb a little more. The performance is still not bad. It's still now maybe 2.25 times as much to go from one thread to 16 threads. But the shape of the curve has changed. It's starting to tail up at the end. And finally, the last test was 10,000 items, really trying to look for races, really pushing the limit here. And you can see was getting large number of races and the curve starts to smooth out. Single mutex for 10,000 items. The behavior is a little better here at the end, but I still don't understand it. And finally, the transactional case. And in this case, the number of rollbacks is very high. The probability of collision and rollback is very high. And so you can see the curve for the transaction algorithm performance is starting to take a little bit of a turn. And now the performance is, instead of a factor of 2, it's a factor of 3. So 16 times as much work now takes 3 times as much wall clock time. And finally, just for giggles, here's a graph that compares the performance for 10,000 items, the previous two graphs on one graph. Here's what it looks like for a single critical section with a single mutex, and here's what it looks like for the transactional algorithm. So finally, these simple tools that I've done, they operate on containers and elements, and they don't require changing the container itself. I'm not changing the number of elements in the vector. There's an assumption that the internal structure of the container is unchanged while transactions are in progress. Consider the case of trying to resize a vector while transactions are in progress. I haven't figured out how to do that yet. Consider the case if you were trying to apply this to a map based on a hash table or a red-black tree, the relationship amongst nodes in those linked structures and how transactions would affect them. Could this be handled better by a per container shared mutex? I don't know. So far, I've only done these experiments with standard vector, and the number of elements is pre-allocated. The vector itself, in a sense, is static. There's no resizes. If you wanted to create a container that's resizable, and I actually did this in the work I mentioned before, I built a homegrown hash table using std vector. Each element of the vector was itself a hash bucket, and the hash buckets contained the actual lockable items. And the hash buckets had member functions for adding and finding and erasing elements. The hash buckets themselves were locked during transactions so that elements within them could be updated. And with a good hash function and a good sized hash table, the lookup was fast, and there wasn't a whole lot of contention from competing transactions rolling back. Finally, downsides of this technique: some threads could starve, some transactions could become stale. Other container types might be amenable, but I've not had time to explore that yet. And of course, there's always lots of room for more work. So I'm a little bit over time. Thank you for attending. I'm going to put the slides up on my GitHub site within the next couple hours, and there's my blog. So I'm going to move to Remo and take a couple questions very quickly. So the first question is, what happens when you roll back? Do you start over with a new timestamp? Yes, By rolling back, you're saying, I am ending this transaction. I'm no longer interested in it. I want to do the same amount of work, but I'm going to create a new transaction. The creation of a transaction is synonymous with getting a new timestamp value. Next question, is it safe to wait on the condition variable of the other transaction while still owning the other elements and not releasing them? Yes, because while you're waiting on the condition, you wait on that condition because what you want to do is you want to update shared state in the other transaction's member data. And while you're waiting on the condition variable, it's safe to do that. You don't have access to it. You can't do anything. When the condition variable is released, and remember, the condition variable is associated with the mutex. When you're released from the condition variable, you are back in the mutex that you've already acquired, and that mutex was a data member of the other transaction. Because you're back in the mutex, you already have the mutex, it is safe for you to look at the shared data that's part of the other transaction. Next question, what happens if two transactions have identical timestamp? That can't happen because the creation of a timestamp is implemented by incrementing an atomic integer. And each transaction begins by incrementing it and getting the value. It's impossible for two transactions to receive the same value from the operation of incrementing that atomic integer. Slide 89. Let me just get to the slides here. Okay, the question is slide 89. What happens if you flow past the while loop? Well, if you flow past the while loop, that means that the owner of the current element, the element's current owner is not the other transaction. The other transaction is released. So you exit the while loop. Remember, when you're at the top of the while loop, you own the mutex. You own the shared state in the other transaction. Because perhaps you've fallen out of this condition variable, and when you fall out of the condition variable, you have the mutex again. If this guy is not the same as what the element thinks he has, you drop out of the while loop, and thus you release the lock. When the lock is destroyed, the mutex is released. You go back up to the top of the loop, and you start a new transaction. And the last question, very quickly, do we need to account for TSV rolling over in our comparisons? Well, I'm using an unsigned 64-bit integer, so I expect the answer to that is probably no. So anyway, so thank you everybody for coming. I appreciate your attention. Have a good conference, and maybe I'll see you in the hallway. Thank you.